Example, you're using the factor theorem to show that this particular expression here is a factor for this polynomial. Now the thing to notice about this polynomial is all real coefficients, which means that there can only be conjugate pairs in this expression. So because we've got, and actually we'll write that here in the main part, so since PZ has all real coefficients, any complex factors must be conjugate pairs. And you might be thinking, how is that helpful to me? That's not helpful at all. But you've actually been given a factor which is complex. So that means we can automatically know another one of those factors. And then because this is cubic, this only has 3 factors. So that should make it easier for us to figure out what that other real factor is. You could also, if you wanted to guess the real factor from here, by using that plus or minus 1 technique, you might find that that works here. So we'll do it that way. For the division, you could actually look in your textbook for that division, but we'll do part A first. So part A says to us, use the factor theorem to show that this is a factor. Because you know that z minus 1 plus root 2i is a factor, what that means is that this equal to 0 is a solution. So that means that z minus 1 plus root 2i equals 0, which implies that z equals 1 minus root 2i. That's a solution to PZ. So because you know that, now what we can do is we can check whether or not that's the case. Okay, so we can check that out. So let's check it by substituting. So P of Z. Okay, we're going to check 1 minus 2i. So I should really, 1 minus root 2i. So let's check what this gives us when we put this into our equation here. So we've got z equals 1 minus root 2i. We should get 0. We'll check it out. So 1 minus root 2i, all of that cubed, minus 3 times 1 minus root 2i squared, 5 times that, and then just minus 3. So with this, you can do this in your graphics calculator if you want to see what you end up with. With something like this, it's generally quicker to do that if you can. So 1 minus root 2i, I'm just going to open my CAS and then just put, I know that's from a different problem. Oops. And I'm just going to do 1 minus root 2i, and I'm going to, remember that for I you need to get that out of the pi menu. I'm going to cube that. Okay, so I can get that automatically, so minus 5 minus root 2i, so I can put that back in. So I know that this part here is minus 5 minus root 2i. Okay, you can do that. And again here I've got minus 3. Let's do 1 minus root 2i and I'll square it. So I'm just going to pick this up and just change the power to a squared. I get negative 1 minus 2 root 2i. Oops. Negative 1 minus 2 root 2i. And of course you could put the entire thing in and see what you get. Just expanding this. Minus 5 root 2i and then minus 3. I can see straight away here I've got a cancellation, minus 5 and plus 5. I've got minus root 2i left over, plus 3. I'm expanding this now. Plus 6 root 2i, minus 5 root 2i, minus 3, and you can see the plus and the minus 3 cancel. 6 root 2 minus 5 root 2 is root 2i minus root 2i. Everything cancels, it equals 0. So therefore, we've shown that z equals 1 minus root 2i is a solution, which means that z minus 1 plus root 2i, remember always opposite signs, is a factor of PZ. So what you've done there is you've used what's called the factor theorem, and the factor theorem tells you that factors are solutions set to 0, so you can solve them for z, and then you should be able to sub back into your original polynomial to find out whether or not that is in fact a solution and therefore a factor. Now the other part of this question says find the other linear factors of pz. Now the first thing that we can do is we can identify a couple of things. I'll just go to the next page. We know already one of the factors. Okay, so we already have this information. I'll just put this on the next page so we can see. So we know this already. What that also tells us is therefore z minus 1 minus root 2i must also be a factor, because we know that these factors occur in conjugate pairs. So that's useful to us because now what we can do is we can actually use that result to try and help us to find other factors. What you can do, there's two ways you can do this. So I'll show you the first method, so method 1. Is the guess the real factor. And so what you can do is look at PZ and actually guess what this is. Now with this one, I can see that I've got a lot of negatives here and not so much in the way of positives. If I can see straight away here that you've got 6 with these two, and then you could have 6 here. I'm going to try z equals plus 1. Remember, try plus minus 1, then plus minus 2, and so on. Work that way with your guesses. But with this one, I actually can tell just looking at it, this is going to be 1 minus 3 plus 5 minus 3 minus 6 plus 6 is 0. So therefore, z equals 1 is a solution. And that means that if z equals 1 is a solution, z minus 1 is a factor. So what you've now done is you've said P of z equals, you found all 3 factors. Because it's a cubic, you should have 3 factors. The factor that they gave you, which is awesome because it's like it's a freebie. The conjugate pair that goes with it, again, that's kind of a freebie because you knew there had to be a conjugate pair. And then the real factor that you can guess. Okay. Method 2, the second method that you can use, which I'll sort of just do part of here, is that you can use the 2 conjugate pairs that you've got here to find a quadratic, and then you'd actually do a division with that quadratic. So what you could do, and I'll just get rid of this part here, for method 2, is you could take your your 2 complex factors, multiply them together. So if you multiply those together, you're going to end up with z squared minus 2z plus 3. Okay, this is in your textbook, so it actually has the full working there if you want to see the full working for getting to there. But you'll find if you expand that, you'll end up with this. And then what you could do is then do a division, and do the division of z squared minus 2z plus 3 into z cubed minus 3z squared plus 5z minus 3. And what you'll find, you need a z here to give you z cubed minus 2z squared plus 3z. Subtraction gives you 0. This is going to be here negative z squared. This will be 2z, and this will be coming down there. That will be plus. That would be minus 3. So we've got nothing happening there. And now if you look at this, you've got negative z squared underneath. To get z squared to negative z squared, you'd need a negative 1. So negative 1 will give you all of these with opposite signs, which is what you want. Oh, that should be, oh yeah, that's cool, 2z. Okay, cool. And then you can see that you've got 0 remainder. So that tells you that in this case, this factor goes into this polynomial z minus 1 times. So that tells you exactly the same thing that we knew from our guess, which is that z minus 1 is a factor, and that these 2 complex numbers are also factors. We just multiplied those complex numbers together to get a non-complex quadratic that divides nicely into PZ. So then you can get exactly the same working off that z minus 1 plus or minus root 2i. So whichever way you do it, the thing to be careful of here is to think about the form of the polynomial. When you're doing a check here for the factor theorem, make sure you check whether or not your factor in the form of a solution is actually a solution to pz, and then finding your other linear factors. I find the guessing is a much faster way if you've got a polynomial with all real coefficients. Otherwise, multiply your complex numbers, factors together to get a non-complex polynomial, and then divide that into your original polynomial to get your final factor. So two different methods that you can use to solve for part B.